Alright everybody, we're going to continue on with our discussion on the multiplicity function and we'll do some practice questions. Alright, so what I want you to do is practice using the multiplicity function for this. You can pause the video, work on this yourself, and we'll go over there in a second. Alright, so here what we have is that we're going to set n equals to 10, and instead of talking about particles being up, spin down, what we're going to end up doing instead is using cards and doing reds and blacks. So those are going to be our ups and downs. Again, as long as we have a binary setup where it can either be one scenario or another, this stuff is going to work. But we're going to pretty much treat all the reds and all the blacks the same. So we're not doing a case of like treating hearts and diamonds and clubs and spades all differently. So we want to know how many possible hand combinations can we have with 7 cards being red. So here we have our equation. Well, this is what's given to us, not our equation. We have to figure out what the half spin excess is. So first we have to take the difference between the number of reds and the number of blues to get the spin excess. We get the spin excess is 4, which means S is going to be half of that number. Alright, so then we can go back. We can use this form since we have the numbers of NR and NB. We could just do this and just do 10 factorial over 7 factorial over times 3 factorial. We may not always be given these numbers. Sometimes we might be given the half spin excess or the spin excess in general, in which case it would have been easier to use the other one. So just keep that in mind that choose which one works best. Not every scenario is going to allow for this equation. Alright, but what we can do is do this. A quick shorthand is just to realize that this 7 factorial is going to cut out everything after the 8 in this top factorial. So we end up getting 10 times 9 times 8 over 3 times 2 times 1, which ends up getting us this, 120. So there are 120 different combinations that we could have where 7 of those cards are going to be red. Of course, this is significantly higher when we consider that there are multiple cases, about I believe 13, for each of those red cards and each of those black cards. So that number for other purposes would actually be much higher, in which case you would most likely want to use something like I said, a more statistical approach in that case. Alright, so here's just a quick little example. Here there are a theoretical scenario where we have, again, a binary system, 10 setups. Here are the total number of states for all the different macro states possible. So again, this is what we end up getting. Now, this was an experimental result that of what you got when you did flip 10 pennies and they were flipped 100 times. So you'll notice that we actually end up getting very similar results here. That when you had essentially 10 heads, which we could consider this, a spin excess of 10, we got the same number. We got well, these are the numbers are slightly off. Multiply everything by 10 almost. But you'll notice that it ends up following a similar pattern, that it goes up in this bell curve type form. Alright, so this stuff does end up matching what we would normally expect. This basically says that there's always going to be that peak right in the middle, that there's always going to be more scenarios where we have essentially equal number of particles going up and down, and that it will end up dropping off more dramatically as you get further and further away from that peak. In fact, the larger the trials, if you did this 1,000 times, 10,000 times, you'll notice that the peak will end up getting much sharper. Um, Now, okay, so what we're going to want to do is that multiplicity function that we have is nice, because it is fairly simple. The problem, though, is that again, we're using large numbers. So that factorial equation will work something like 50. You know, doing 50 particles would definitely be a pain in the butt to do by hand, but it's not what we would expect for a gas. And anything even remotely higher than that, 1,000, let's say, which is still fairly small for the number of particles in a gas, uh, would not work because we can't really do factorials for higher numbers like that. So what we would do instead is we have to simplify it by getting rid of the factorial. And we're going to do this by taking the log of this multiplicity function. One thing to note is in the book, they use log as base e. Essentially, it's ln. So again, keep that in mind, that technically these are all ln functions. All right, so one thing that we end up seeing is this, that when we take the log of the multiplicity function, due to the log function where anything that is divided can just be subtracted, that formula that we have with the factorials simplifies to this. So we end up getting log n factorial minus log n up factorial minus n log down factorial. Now what we have to do is we have to use something called the Stirling approximation. This is definitely important, so you want to make sure that you're able to do this yourself. But basically what it is approximating logs of factorials. Now the approximation is this. So when you have n factorial, this is the equation that this is approximately equal to. Now taking the log of this, we'll end up simplifying to this. So yeah, we end up getting the 1/2 gets pulled out to the front, log 2 pi. The n can actually be brought in with over here with this log n. And then we get the minus n. Everything past here, it's too small. It's not even worth mentioning. So that's why it doesn't continue on forever. It kind of drops. Now, I do want to point out that there is another form of the Stirling approximation that you'll see later on. But this is definitely one form that you want to be able to know. All right, so bringing this back to kind of what we had before and trying to, simplify things a bit, we can replace all these n's with an n plus n down. I tried to do this so that it was more visually appealing by having different colors. Also, I wanted to point out that we are going to add in some of these terms, again, just to make our lives a little bit easier. This is just, because these kind of cancel each other out. It's going to allow me, though, to kind of bring it in with this term over here. All right, so what I end up getting is this. So this minus 1/2 log n term actually gets brought over with this log term. So that's where that 2 pi over n comes from. This one is going to be brought into here so that we have an n up plus 1/2, n down plus 1/2. We could do pretty much the same thing for the other two parts with the n up and the n down. Though we don't have to actually do anything special with this. Going back to our multiplicity function where we had the log, I know this looks really long and messy, so just bear with me. but we take our first simplified form of the Stirling approximation, plug it in for that log n factorial. Then we have the n up approximation, the n down approximation, all being combined together. And now we can start kind of simplifying and getting rid of terms. So for example, uh, all these half log 2 pi's can actually be brought over into here, and we end up getting this. So these are just these first parts in all three cases brought together. Then I can also combine all the n ups together. So we have the n up plus a half here, we have the n up plus a half over here, gets brought over here. All the n downs get brought together as well, and we end up getting this. Now, before we continue, one thing I do want to point out is this is something that you aren't going to have to do too often. There is another, like I said, there is another Stirling approximation that you will kind of have to uh, use in order to kind of come up with a better or approximated multiplicity function for different scenarios. But you shouldn't have to do something like this specifically. Okay, so coming back to here, when we take this and we again simplify everything, we end up getting this. So these 2 pi and a halves get brought into here. These can combine into this and that. All right. So what we're also going to do is we're going to use another approximation, going back with the log, that log 1 plus x is equal to this function when x is really, really small. So in a case like this where we have n up divided by n, that would kind of end up working. So here, this will end up being equal to 1 if we take the 1 here, 1 minus n down over n. So from here, I can also actually replace the terms like that. So it ends up changing from this form into here. From this actually will get us allow us to use this approximation here, because now it's written in a form of 1 plus something really, really small. Unfortunately, something like this wouldn't always be small, or not in all cases. So we kind of had to go back to using the whole 2s in for the n down here. All right, so taking this and using this function, this simplifies to look something like this. Now, once again, notice that we're dropping all these higher terms because of the fact that 2s over n is going to be once again so small that anything higher than to the square would just make the number so inconsequentially small. So we can just stop here. Likewise, we could do pretty much the same thing for n down over n to get this. Pretty much no real big difference, except a little sign change here. Bringing this back to our original equations, we end up getting, taking this and plugging into the first part, this into the second part, or I guess technically third. We can then simplify a bit and again move some things around. Here we're going to kind of want to recombine some of these terms with the n downs and n ups, so that we can, when we combine this, we'll actually end up getting a full value of n, like what we did here. So now this becomes n plus 1 and n plus 1, or no, sorry, this would be 2s, this would be n plus 1, like that. And once again, just keep playing around and moving things around and simplifying and yada yada yada. And what we end up getting is this. So this ends up being a somewhat more simplified form of that log of the multiplicity function. Now notice it's not yet purple because we're not done yet. So we want to get rid of the logs. Oh, I guess I don't show the work here, but we could get rid of the logs the same way we did before, or how we normally would get rid of logs, by raising both sides to the e. So raise this to the e, raise this to the e, and it just kind of brings everything together. So our final multiplicity function is given by this equation. So our multiplicity function can be simplified to being this term, n comma 0, times e to the negative 2s squared over n, where this term is going to be equal to this junk right here. Now what this is actually referring to is just the total number of microstates, it's the multiplicity function for the middle, I guess, when you have equal numbers of ups and downs, or when the spin excess is 0, if that kind of makes sense. So we're using this as the peak multiplicity function, the peak number of microstates. And then any other microstate would be this peak number times this e function. So we can see from here that this is actually following a very good Gaussian distribution, which is exactly what we kind of saw before, that bell curve, and that the more values that we have for n, the quicker and sharper it drops off from that middle 0 spin excess. So here, if we tried to do n equals 50, when we use the actual equation, when we use the actual, with the factorials, we end up getting this as the total number of states available in that central point where the spin excess is 0. However, if we use our estimation we have here, we end up getting a number that's slightly higher than that, 1.27 versus 1.264. So we still get a fairly good enough number that we can use it, but it's not exact. So this is actually one thing I want to point out, is that when you have a small number, when you are actually capable of doing a factorial on your calculator, do this. Use this function to use it. If you find that you can't do the factorial, you're doing things with numbers in the hundreds and the thousands and the millions, then you're allowed to use this. So just be aware. If you get to a point where you can't, always start with the factorial, but if you find that you can't use it, then you're allowed to use this estimation, because as it says, it's an estimation. And yeah, these numbers will get drastically closer as we get higher and higher in the value of n. All right. Another thing that we could talk about are things like average values. So what we can talk about is something with probability. Now, if we have some sort of function, the probability, and we say that the probability of that function occurring is equal to this, p at some spin excess, then the average value will actually end up being the sum of all the functions times by their probabilities at the same states. And it's set up and normalized in such a way that if we just summed up all those probabilities, we should end up getting 1. Now, before I continue, I do want to point out this is the concept behind a weighted average. So if you've ever taken an average of something where not everything is the same, something like, actually, like when I do for your tests, each of your test grades are weighted, or not just tests, but all the assignments, the homeworks, the test, the final, when I go to find your total average grade for the class, I use a weighted average. I multiply all those numbers by the weight that it has in your grade, 25%, 35%, 10%, and I add them all up and I get your average value. It's the same way here. So yeah, this is what's called a weighted average. But the way that we represent average values is mainly using these brackets. I mentioned that because this is going to come up a lot. All right. So in this scenario, though, we're not going to have a case where there's different probabilities. You might see it later on where some of them are weighted differently, but like I said, not likely here. So we're going to assume that the probability of the particles going up is also equal to the probability of particles going down. So what we end up getting is this, that the total probability of a state occurring would be given by this function. Now recall before how we found the probability of that one state before. I said that we took the number of states that we can get in that first scenario is 1, and we divide it by the total number of states. Well, we do the same thing here. If we want to know what is the probability of us getting a, let's say, spin excess of 0, well, what I would do is I'd figure out, well, how many states are available that would give us a spin excess of 0. And then I would just divide it by the total number of possible states in general, and that would get me the probability for that specific case. So bring this back, our average function equation will look like this. Now, you might be wondering, well, what is this function? It's anything. I want mass. I just put an m in there, and there we go. So this, average value function is a stand-in for literally anything that we want. We want to know what the average speed is. Well, I just put a speed in here, and I do pretty much the same thing. All right, so here's a question. Try using some of the things that we learned before. Pause the video, work on this stuff, and we'll go over in a second. All right, here we have a drunk that's standing by a lamppost, and he's able to take steps of equal length, either left or right, and we're going to assume that they're equal probability. So we want to know what is the probability where the man's going to end up being some n steps where n's going to be even or n's going to be odd. So the probability of him returning back to that lamppost. So first, if it's even, it can return if the number of steps he takes right and the number of steps that he takes left are equal. So that both numbers will have to be 1/2 of that. So the probability will be the total number of states divided by the multiplicity function divided by the total number of states. So what I can say is this, that it's going to be equal to, well, this is the 0 spin excess, if you will. When I take this and I plug in the 1/2 n, I'll just get this. There's really not much else that I can do. I can't really simplify this any further. Now, part B is a little bit easier. What if it's odd? It's impossible because there's always going to be one extra step, either left or right, and he can never return to that lamppost. So yeah, so A is the only one that can actually be solved. Now there is a variation on this where instead of it being equal probability, it ends up being an unequal probability. Maybe he wants to go right, but he keeps stepping left every now and then. So we could ask the same question of what's the probability of him returning to that lamppost? But we would have to change some of our equations here in order to take into account that there is a new, bias to the steps that he's taking. All right. Oh, This is actually one thing that I want to, that is definitely good to note is that if we consider a case of a function being equal to s squared, one thing that you want to make sure that you know is that the average value of s squared is not the same as the square of the average value. They're two different things. You know, if you take an average and then you square it, it's different than if you square all your numbers and then you average it. If you don't believe me, you could try yourself and see how that works. But what we'd end up getting is something that looks like this. Again, this is just the function s squared. This is our approximated multiplicity function, and this is that total number of microstates. This term we could pull out, so we're just left with the s's in here, and we get this equation. We can replace the sums with an integration, and then just say that it's being integrated with respect to ds. Now, this is, how typically with integrations, one thing that you always want to do is try and find a way to simplify it by kind of getting rid of some useless things and trying to rewrite it in a simpler way. So what we can do is just replace this whole term with an x squared, and then we'd have to replace ds with this. So our integral ends up turning into this equation, which is actually something that we can simplify. It ends up combining all this, simplifying to n over 4. What this actually is going to give us is something that we call the root mean square of the spin excess. So again, some of you might have heard that term before, root mean square. It's kind of hard to pinpoint exactly what it is. There are two common cases where you see root mean square in circuitry when you're trying to come up with a usable value for the for like the average current or average voltage for a AC circuit. Another time where you see root mean square would be RMS velocities, root mean square velocities, when dealing with gases. Once again, as like a usable value for gas. Here, basically, it's just relating to the spin excess, and that it basically ends up equaling this rad n term. We can use this to talk about something called factorial or fractional spin excess being equal to 1 over rad n. Basically, all this is really telling us is how wide that that peak is based off of the value of n. So as the value of n gets bigger, the peak of that term is going to end up getting smaller and smaller. That ends up becoming more and more drastic of a drop going from the middle to one of the next spin excesses. So that's what this is all getting to. The reason why we can't just do an average of the spin excess, and the reason we have to do a root mean square average is because, and this goes back to some of the examples I gave before with the RMS velocity and currents, is that because there are equals amounts of spin x's that are positive and negative, taking an average will always be equal to 0. So in order to figure out actually a usable spin excess, we have to do a root mean square average. So here, this kind of just puts it better into words that if we consider a case where we have 10 to the 20 particles, which I think is still not a huge amount, we end up getting that the fractional spin excess is 10 to the negative 10, basically referring that to the width of that distribution of spin values is going to be very, very small for this large number of particles. So that's really what we use this for, as a proof of what we were saying before, that it drops off very quickly and very sharply as we get further away, especially the larger the number. All right. Another thing we can talk about is something like dealing with the energy in the binary magnetic system. So here, um, this is just saying that if we end up adding in a magnetic field, we can figure out the energy being equal to this. That's just the equation. Um, it could also be rewritten like this, with, by saying that if we have multiple magnets, the total energy would be the sum of the energies of each of those magnets, and pretty much goes back to kind of what we said before, where we could just replace that with Sm, 2Smb, and then this whole term just gets replaced with the total magnetic moment. You know, just kind of goes back to a lot of the things that we said. A lot of this is kind of rehashing things that we've kind of already mentioned, like how the energy is going to change by a factor of 2m, um, or the energy changed by 2mb, sorry, for each different magnetic moment. Yeah, so the difference in the energy value is going to be 2mb. All right, here's a practice question that you could work on. Pause the video, work on the stuff, and we'll go over in a second. All right, so here we're going to use the Gaussian distribution, basically that approximation. So the probability, I guess, is now going to be 1.3%. We get that by taking the function that we have and just plugging in that term here, and then we're going to multiply it by 2 to the n. We're going to take the n to be 400. We are going to have to figure out what that half spin excess is. The spin excess, a very quick and easy way of figuring that out is by just taking the difference between the average number, the half number, and the number we have, and we end up getting 15. Essentially, this is the same thing. It's written differently, but this is what we had in that first slide of n up equals 1/2 n plus s. So you could have used that as well, but you'd end up getting that s is equal to 15. Putting all this stuff together, that gets us that the probability is 1.3%. All right. And these are all the things that we mentioned. The multiplicity function, the general form of the multiplicity function that we can use for small numbers of n, pretty much anything less than 100. For numbers that are much larger, we can use this Gaussian approximation. And then this, like I said, kind of plays a part later on, but that we can figure out the average value of the spin excess, or the spin excess squared, the RMS value, by using integration to get 1/4 n. Then we also talked about the energy for the different spin excesses, and that's pretty much it. There isn't going to be a homework for this. This is actually the first lecture where we're actually not going to be doing homework, but in later lectures you'll notice that there's going to be a homework section at the end of the lecture. So for now there is no homework for this first chapter. If you have any questions, please let me know, or you can save them and wait until the office hours. Otherwise, I'll see you later.